All right, so this first page, I'm not going to hand out a book to you, okay? I am like anti-book because when I was in middle school and elementary school, somewhere around that time, I was carrying around so many heavy textbooks that I popped a few vertebrae in my neck. Okay, it's not like they were sticking out of my neck or anything, but it was kind of painful. You know when you wake up sometimes and you have a stiff neck and it hurts to turn it? That's basically what happened. And somehow it came back that it was because I was carrying too many books in my book bag. So I am completely anti-book. Instead of giving you a textbook to lug back and forth, I'm going to give you paper copies. Is that okay? Does anyone prefer a book? If you do, I can give you a book. No. Okay. So what I'm giving you today are the first 2 units that we're going to cover this year. Our first unit is very short, just very review type, and then we're going to dive into kind of the first real section of calculus. So this first page is kind of a cover page for you to put in your folder so you know it's your math binder. Okay? The next page is the table of contents. Okay, so basically whenever we finish a unit or a chapter, I will give you the new unit or chapter the next day. So eventually, by the end of the year, you're going to have your own calculus textbook with every single problem worked out. I think that's a wonderful resource to have for any future mathematics course that you might have to take. Okay, you're going to have your own workbook, textbook at your disposal. Okay, so instead of giving you all, what does that say, like 400 pages at the end? Today, we're going to take it in baby steps. Okay, I overwhelmed you with the other papers, right? I didn't want to overwhelm you completely with 400 more papers. Okay, so there's your table of contents. I hole punch everything so you can just insert it into your binder appropriately. You'll also notice at the bottom of the page there are page numbers, so you can keep things in order that way too. All right? All right, so our first unit that we're going to talk about is function analysis. For each unit, there will be some type of table kind of outlining how things are going to go for that unit. On the in the first column, this is kind of my idea how long each section is going to take. Okay, this might not be accurate. Sometimes we might have to spend more time or less time, but this is my idea about how long it might take us. You also see the objective, like what we're going to do on those days, and which pages we're going to be working on in this kind of paper textbook I give you. Okay, so today we're going to analyze some graphing characteristics. We're going to plot some points. We're going to talk about different functions. We're going to see how much we can determine about a graph based off of how it looks. And then we'll eventually get to our favorite ever unit circle, right? Yeah, that'll probably be tomorrow. Okay? So, we're going to get started on page 7. If you have a graphing calculator, it might not be a bad idea to get it out because we can review some buttons to use to help us. Or maybe we can do this the old-fashioned way, use our original calculator, our brain, right? Okay. Now, I've had all of you before, so you know if I go too fast or you don't understand something, you better tell me or raise your hand, right? Okay. Don't be afraid. Don't be scared. We're here together, okay? You let me know. Actually, I haven't had you before, but I know you, okay? But we're going to be good, okay? All right, so let's take a look at our first one. Given below are tables of different functions. Okay, we know different functions. We have lines, parabolas, cubics, rationals, square roots, exponentials, a whole bunch of different types of graphs. We're going to try to classify each function by its type. We're going to sketch a picture. We're going to try to figure out as many properties as we can. And if possible, we're going to try to figure out the equation. Okay, now we're given a table of values. What do you want to do first with that table of values? Anything. This is very discussion based. You guys can just shout out if you want to. What do you feel like doing? Graph it. Let's plot some points. All right, so take the time. Go ahead and plot some of those points. we're going to plot the points to try to get a picture. That way maybe we can figure out what type of function it is. So some of them might be as to where they might be. Some of them might be off your graph, but that's okay. After plotting those points, what type of function does it look like we're going to have? Say it again. Linear. All right, so let's connect them with a straight line. All right, so let's go ahead and label this as a linear function. All right, so classify each function by type. There we go. Sketch a graph of the function. There we go. Then state as many specific properties, including the equation if we can, of this type of graph. Okay, so if this is a line, what are some different properties that a line has? Okay, this one's going to be a little hard because it's our first one, but once we do one, you'll start to see what I'm kind of looking for here. What do you think, Dan?
It only has one root. Y intercepts the x-axis once.
One root. Okay, so root meaning x-intercept somewhere right there. Okay, so maybe our first bullet point, 1 root / x-intercept. Is there another name we normally use for a root x-intercept? Yeah, a 0. Good. All mean the same thing. Like math isn't confusing enough. We have 3 words that mean the same thing. All right. Anything else special about the graph of a line? Different properties, characteristics?
It's straight.
It's straight. Okay, so if it's straight, let's go ahead and write that down. But the word straight, mathematically, different way of thinking about this. We have a constant slope. Isn't the rise and run the same all the way through that line? You go up and over the same amount every single time. That's what's making it straight. Okay, you have that constant slope, that constant rise over run. Anything else? Do we have specific equations of lines, like forms of lines?
Y equals mx plus b, which we know that the b is -3, as b is the y-intercept.
All right, so this is going to help us write the equation. Maybe we can determine some certain thing or certain parts of this equation based off the graph. Do we know what the name of this y equals mx plus b is called? What type of equation or form of equation that is? Slope-intercept. Okay, so now that we have slope-intercept, maybe we can identify the b and the m to help us write the equation. What does the b represent? What did you say it was, Dan?
The y-intercept.
Y-intercept, okay. And what does the m represent? Slope. Okay, so we have a picture of it. Can we identify either of those? Dan, you gave us one of them before?
Yep, the y-intercept is -3.
-3. Okay, and how can we determine the slope of the graph? You could do it 2 different ways. Yeah.
You could take 2 separate points and do the following equation of y2 minus y1 over x2 minus x1.
All right, so one way, you could pick any 2 points you want from the table and use the slope formula, y2 minus y1 over x2 minus x1. -2/3? Okay. How can you determine that same slope, -2/3, based off the graph?
2 points.
Pick 2 points. Okay, so 2 really, really good points. Like not these fraction ones, because we're not quite sure where those are. You got to pick 2 really, really good points. So ones that actually go through kind of the crosshairs or tick marks on your graph. So it looks like we go down to right 3. So our slope would be -2/3. Okay, so now that we identified those two different pieces, that means we can write the equation of this line. Notice specifically, based off the table, that the name of this function is f of x, capital F of x. So we'll say capital F of x equals negative 2/3 x minus 3. There's the equation. Perfect. We doing okay so far? All right. What about some other things about lines? What's the domain of a line? How far left it goes, how far right it goes? Yeah.
The domain is all real numbers.
All real numbers. Do we know?
As is the range.
As is the range, yep. Do we know a symbol? You can write all real numbers.
Let's say R.
Yes, okay, so we can say, you can actually write out all real numbers, okay. A different way you can state that same idea is like a double-stemmed R. That's the mathematical notation that means all real numbers, okay. What if you wanted to use interval notation, like parentheses or brackets? If you could go everywhere on the graph, yeah.
Parenthesis, negative, infinity, comma, infinity, parenthesis.
There you go. All right, so all of these different notations mean the same idea, all real numbers. You can plug in any x value you want, and you will get out a y value, okay? You can pick any number you want. What about, are there any discontinuities on that line? Do we know the different types of discontinuities? Holes, that's one of them.
Jumps.
Jumps, that's another one. Everyone's favorite swear word in math?
Asymptotes?
Asymptotes, yep. Okay, do we have any of those?
No.
No. So no discontinuities. Perfect. All right, there's one more thing I think that would be important for us to write down for this one. So we talked about slope-intercept form. That's one way you can write the equation of a line.
Standard.
There's two more. We have standard form. Do we know what that equation of a line looks like?
AX plus BX equals C.
There we go. AX, close. AX plus BY equals C.
Yes.
Perfect. Okay. A, B, and C are whole numbers, nice numbers to work with, not necessarily fractions. And then there's another way you can write the equation of a line. Kind of the less popular one, but we're going to use it all year. Yeah. Point.
Oh, we're going to use it all year.
Oh yeah, you're gonna learn to love it. I'm going to tell you right now. You're going to learn to love it. Point slope form.
Point slope. Oh yeah, that's right.
Yep, point slope form. What does that look like?
A mess.
Kind of. Y. We're whispering it. Y minus
Y1.
Y1 equals? There's an X. M comes
M
first
X.
though.
Yeah.
M times X minus X1. All right. You are going to love point slope form this year. I promise. Because you can leave, if you know a point and a slope, you can plug it in, you can leave it like that. I'm not going to make you manipulate it somehow. I promise you're going to learn to love it. All right? Do you kind of see what I want us to do with these different examples? We're going to analyze different characteristics,
Yes.
okay? Different properties. Let's try our next one, okay? What do you feel like doing? Graph it. Let's plot some points.
It's positive.
Yep, +5, thanks.
Interesting.
Yeah. All right. Type of function, what do you think it looks like?
quadratic.
It does, right? Kind of looks like a U. I mean,
That looks more like a V.
doesn't it? Okay, do you see how this side is very straight, constant slope,
And that's
right?
an absolute value.
Oh, there we go, V-shaped graph. Absolute value. All right. So let's try some characteristics here. Maybe you can look at the linear example we did to list some ideas for this one. Anything whatsoever? Yeah.
There's 2 roots now.
Okay, so in this particular example, okay, in this one we have 2 roots, okay, but does every absolute value have 2 roots if you were to graph it?
New.
No. What are some other possibilities? It could have none, right? What if I took this V shape and shifted it up all the way up here? It wouldn't touch the x-axis ever, right? What if I shifted it up 3 spots? Wouldn't this vertex just touch the x-axis? So then you'd only have 1, okay?
Multiplicity of 2.
What was that?
Wouldn't it be a multiplicity of 2?
Multiplicity of 2, yep, because we just bounce or just touch it. Perfect. So this example has 2 roots, but that's not always the case. Could have 1 or 0. All right. Any other characteristics?
The slope is reflected along the y-axis of -2.
Okay, it's reflected, so it's the same. Notice how this slope and this slope are exactly the same, just going in different directions, right? One side is going down, the other side's going up. So we still have constant slope, but opposite slopes on each, we'll call them legs. Okay? Anything else? Can we figure out the domain? Can we write an equation?
Y equals absolute value of x.
All right, so
I should shove an m in there.
okay, we could try. Notice how this function's called g of x. So that's what, instead of y, we'll call it g of x. We know we need absolute value bars in there somewhere. All right. Where does an absolute value graph typically start? 0, the origin. Okay, everything normally starts at the origin. But notice how this vertex doesn't really start there. So that means it was moved, shifted somehow. Can we describe how it was shifted?
Left by 2.
Left 2 and down 3. How do those shifts or transformations show up in an equation?
Any shift left or right is shown as the opposite, so because it's going left, it would be a positive, like a +2.
Okay, we got an x plus 2 on the inside of those absolute value bars. What about the down 3? Outside. We're good back there, ladies? High-fiving? Perfect. All right. Now, Dan before mentioned something about the slope. Now, the typical slope of an absolute value is 1, like up 1 over 1, up 1 over 1. Did that change for this example?
No.
You sure? If I go up 1 over 1, I'm right here.
Oh, that's what you meant.
Uh-huh.
I thought you meant like the form, not the actual number.
Oh, no.
2.
Sorry. Can we figure out what the slope would be? Notice how if we start at the vertex and pick one of our other points, we go up 4 over 2.
Yep.
So the slope is
Just regular 2.
just regular 2, 4 over 2. Okay, so that's kind of our vertical stretch or our slope in this case. We got that 2 multiplier out front. So there's the equation of this absolute value. Any discontinuities, holes, asymptotes, jumps?
No.
No.
technically is one, but not as it would be described.
Where?
Well, it's more of a range feature in the sense that the minimum range is -3 and nothing goes below that.
Perfect. Okay, so this one's a little different than the line. Okay, the line, it can go all the way down and all the way up. So the range is all real numbers as well. But this one not so, because the lowest this graph goes is -3. So if you wanted to write something down about the range, we can. Let's go ahead and maybe do the domain first. Domain, how far left and right could we go?
All real numbers.
All real numbers. Okay. This range is a little different instead of all real numbers, so maybe we'll classify this one as well. What's the lowest this graph can go and the highest? Go ahead, Anastasia. And infinity. Parentheses, brackets, where do they go? Uh-huh. Perfect. All right, so that's interval notation. You give a beginning and ending value. Okay, but you could also represent this in an inequality form, like greater than, less than. If we're talking about the range, those are y values, and we want all the y values bigger than -3. So in other words, greater than or equal to. Those are two different ways you can write or represent the range. I think that's good, but is there anything else you guys want to add? Notice? No? All right, let's check out our next one. What do you feel like doing? Plotting some points? Get a picture?
Yep.
Oh, man. We're still here a little bit longer, I think, right? Yeah,
Oh yeah, that's the lunch bag.
that's the first one. What kind of function do we have?
Which right?
Quadratic. Parabola, good. Quadratic. All right, so we have a U-shaped parabola. Looks good. All right, characteristics.
2 roots.
2 roots, but
Could be 0 or 1.
could be 0 or 1. Okay, same reasoning as the absolute value. If you shifted it somehow, it may or may not touch the x-axis at certain points. Anything else?
The slope is not constant.
This-
It is negative.
All right, so we could have various slope values. For instance, if you were to pick some points, if you look at the vertex and the next point right next to it, notice how that slope is -1. But if you pick that point and the next one, that slope is down 3/1, which would be -3. So you have various slopes, okay? That's what's causing the curve, the curvature, or the steepness, okay? So various slopes. What'd you say it was in this case?
It would be negative.
Okay, so the initial, right, is definitely negative because our graph is going down on both sides. Great. Anything else? Characteristics. Domain, range, discontinuities, equation.
The equation would be h of x.
All right, so this function is named h of x. If this is quadratic, we need a quantity squared. And we're going to use the graph to help us fill in the different values. All right, so again, typically a quadratic starts at the origin. X minus 1, good, it was moved right 1.
Then plus 4.
Up 4. And since our graph goes down, negative out front. Perfect. All right.
The range.
Okay, let's try domain and range.
would have the smallest point of negative infinity with a highest point of 4, 4 being in brackets and negative infinity being in parentheses.
Okay.
The remaining would be all real numbers.
All real numbers. Perfect. All right, so we can go as far as we want left and right. We can choose any x value we want to plug in and we'll get an answer. But our answers, our y values, are only going to be numbers between negative infinity and 4. Okay, because the 4 is the tallest it can go. You can touch there, so we have a bracket. All right, anything else?
No discontinuities.
No discontinuities. All right, so this is quadratic. There's another way, okay, the standard form way of writing a quadratic equation. Okay, we used kind of the transformations to help us write this equation. But if we were to get rid of the parentheses, combine some like terms, what would the standard form quadratic equation look like? Yeah.
ax squared plus bx plus c equals y.
There we go. Ax squared plus bx plus c. Now, if we have a standard form equation, there are two things we can do to it to help us solve certain things about quadratic equations. I know that's a very vague, we'll put one up here. If I gave you an equation in standard form, is there a way you could manipulate it?
Factor it.
You could factor it. You could try to factor, okay, sometimes you might not be able to. And if you factor it, normally you get these different parenthesis groups. We remember how to factor, right? Okay, we're going to be doing that a lot this year, bless you. Let's say factoring isn't an option. What else could you try?
We've got to do quadratic form.
All right.
Which would be
Oh, do we remember it?
negative b plus or minus the square root of b squared minus 4ac.
So, hold on. Slower. Negative b.
Negative b
Uh-huh.
plus or minus
Okay.
the square root
Yep.
of b squared
Yep.
minus 4ac
Uh-huh.
all over
Yep.
2a.
2a. Awesome. What does that quadratic formula equal? What does that number represent or give you?
The roots.
The roots, aka x-intercepts. So the quadratic formula is always x equals. It gives you the roots, x-intercepts, zeros of your graph. So in this case, we would get -1 and 3 as the answers from the quadratic formula. Perfect. Do we remember the quadratic formula? Did anyone ever sing you the quadratic formula song? What was that? Do it? Oh gosh, okay. Do we know Pop Goes the Weasel? Like bum ba dum ba ba da ba ba.
Yes.
That? Okay. The opposite of b plus or minus the square root of b squared minus 4a and c all over 2a. Burn it in your brain, okay?
You should send that to your babies.
My baby? I already have. By the way, I don't know if you guys remember or not from last year. I'm pregnant, right?
Yep.
Okay, so you're not going to see me a little bit this year, but I will be back before the year's over. Okay, I'll be gone January, February, some of March. Okay, but I'll be back. All right.
Don't have them on January 5th. That's mine.
No, December 11th is my due date. So I'll miss like a week, and then you guys are off for Christmas, and then we'll go from there. Okay? Yeah, I know, me either. It's another boy. So, mom of boys. Any advice, gentlemen?
Don't have a dog.
Spank.
Don't have a daughter. Run, maybe?
Discipline.
Discipline.
Oh yeah, just
All right. Anything else for quadratics? No?
love.
Lovely? All right, let's try the next one. We're getting good now.
The only reason I said is because I have a younger sister.
You have a younger sister?
She's a freshman now.
How's she handling her first day? Have you seen her yet?
She is excited.
Okay.
She's nervous.
All right. Type of function. A little tricky. You draw a graph from left to right. Okay, so notice how they're telling you at -4, you don't have anything, so there's no graph there.
Is it a log function?
If we had more information, maybe logs continue down this way, but we're not sure of that. The only point we know is that beginning point.
Okay, that is the square root.
Square root. All right, so whenever you're dealing with this table, okay, it has that undefined word in there. That means there's no graph. There's no point at that location. So it could be a hole because there's no graph at that point. It could be an asymptote because there's no graph at that point. But it also could just literally mean the graph doesn't go that far. Okay, it's not all the way over to that side. So at -4, we don't have a graph there. Maybe we'll just not represent a graph there. And we don't really know what's happening on the other side either, so we can't really plot anything there. We're just left off with this square root type of graph. So let's talk about some characteristics.
One root.
One root. But if you kind of shifted it, moved it up or down, would you get more or less?
You could only have none.
Could have none.
Yep.
All right.
Various slopes.
Various slopes, yep. Okay. If your line, or not your line, I want to say line, if your graph is curved in any way, you have various slopes, okay, because that slope change is what's causing the curvature. If you analyzed it, our initial slope is 1, our next slope is up 1/3, so that's 1/3. Okay, notice how the slopes are changing. Anything else? Equation, domain, range, discontinuities? No discontinuities? We'll try domain, range, and the equation.
Well, you definitely need a square root for that j of x, and you definitely need an x in that.
Yep.
Considering that it is leftward, it would be plus 3
Yep.
within the square root.
Perfect.
And outside of that, -2.
-2. All right, so just like every other graph starts at the origin, notice how this beginning point, though, does not start there. It was moved left 3, down 2, so we can represent those transformations appropriately. What is our initial slope? From the beginning point to the next point,
1.
it's just 1. So, I mean, you don't have to write 1 there if you don't want to, okay? But if that initial slope was something different, you would have to write that vertical stretch in there. Do we need a negative at all?
Nope.
No, this wasn't flipped in any direction. Perfect. What about domain or range?
The domain and range are both not all real numbers.
Not all real numbers. Okay, so let's talk about domain. If we're looking at left to right, okay, on the x-axis, where's the beginning x value and ending x value that this graph would have? -3 with a bracket,
And then infinity.
and to infinity, perfect.
And then -2 with the bracket.
And infinity, perfect. We're hanging in there? Perfect. I believe the bell's going to ring in a little bit. Okay, so we'll stop there for today. We have a few more graphs to do, and then tomorrow we're going to get into our lovely unit circle.
I remember this. I did one over the summer.